Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. Before we go any further, I want to remind everyone that we're dealing with a physical object, a quadrupole magnet that has a width and a height and a length. And so we're trying to keep track of the motion of the protons through the quadrupole magnets in the Fermilab booster proton accelerator, so that they don't start colliding up against the walls of the quadrupole, which would not only reduce their ability to be a beam of collimated protons to collide with another beam once introduced into the tevatron, to collide with another beam of protons. That would totally not work if the protons started to collide with the sides of the quadrupole magnet. So it's very important to be able to derive the equations of motion, which is a major part of being able to track the trajectory of these protons as they circulate around the particle accelerator. So what I want to do right now, I want to bring up the picture of the quadrupole magnets, okay? Just to remind all of us, this is a physical issue. The dimensions of the quadrupole magnet, right? To keep that beam of protons, highly energetic protons, collimated as they travel around the booster synchrotron. Okay, here we go. All right, here's those quadrupole magnets, right? That circulate all the way around the booster synchrotron and the tevatron at Fermilab. All right, now one thing I want you to notice is that you have a quadrupole up here and you have a quadrupole down there. So you actually have two quadrupole magnets, all right? And there's a reason for that. And we're gonna get to that a little bit later. But again, keep in mind, as the protons travel down the tunnel of the booster synchrotron, they have to stay collimated. And based on the dimensions of the quadrupole magnets, that beam of highly energetic protons has to be such that it doesn't start to collide with the sides of the quadrupole magnets, okay? Very practical reason for wanting to track the betatron oscillations of protons in a synchrotron. Okay, all right. What we're going to do now, we're going to go back to the mathematics, okay? We got to get to those equations of motion so that we can track the motion of the protons as they circulate around the synchrotron. All right. All right. Last week, we left off with this equation right here, okay? M d squared x over dt squared plus EV kx equals to 0. All right? As a review, we found out that the force, mass times acceleration, right? F is equal to ma. In the case of a particle accelerator, that's equal to the magnetic force that the magnetic field of those quadrupoles are applying on the protons as they circulate around the synchrotron. All right? We did some algebra, and we came up with the equation that mass times acceleration, ma, is equal to the charge of the proton, which is E, times its velocity, times the vertical component of the magnetic field of the quadrupoles. Okay? Because right now, we're talking about motion in the x direction. Okay? The horizontal direction of the proton. Remember, phase space, horizontal, x-axis, vertical, y-axis. And the z-axis, that's the axis of motion that the protons are traveling in as they circulate around the proton, circulate around the synchrotron. So x and y, right? Perpendicular and horizontal phase space of the proton. And phase space, right? We got to keep that phase space as small as possible, right? We got to keep those protons as closely collimated as we can, right? We can't go too far in the horizontal, the x direction, with respect to the trajectory, right? That'll get close to the sides of those quadrupole magnets. And we can't go too far in the vertical direction, right? Up and down, because that'll get close to the top and the bottom of those quadrupole magnets, right? So we got to keep that beam collimated. It's very important to know the position of the proton in the horizontal direction, the x direction, and the vertical direction, the y direction, so that the protons don't get too close to the sides of those quadrupole magnets. All right, so let's go back to this. All right, so we have mass of the proton times its acceleration. And remember, this is along the x-axis. The same applies to the y-axis, okay? The same thing applies horizontally and vertically to the trajectory of the proton. So its mass times its acceleration in the horizontal x direction, plus the charge of the proton times its velocity times the vertical component of the magnetic field. Because remember, the vertical component of the magnetic field acts on the horizontal position of the proton. All right? Okay. And we set that equal to 0. Now, to this equation. All right. M is mass. D squared x over dt squared, it's calculus, all right? It's a differential equation. In calculus, the way you express acceleration is with a derivative right here. Now, from physics, from experimentation, we know that distance is equal to velocity times time, correct? We know that the distance that you walk is going to be equal to how fast you're walking, the velocity or speed, and the time in which you're walking, right? Distance is equal to velocity times time. You see how physics uses mathematics to describe the phenomena in our natural world, okay? Makes perfect sense, doesn't it? Distance is equal to velocity times time. Okay, now, in calculus, when you want to describe the velocity of an object, you take the derivative of x, okay? The derivative of x with respect to time, all right? That's velocity. And if you want to get the acceleration of an object, you take the second derivative of x with respect to time. So what we're saying is that you start out with the distance and its relationship to time, dx with respect to dt, the change in position of an object with the time it takes for its position to change. That's velocity. That's dx over dt, okay? And now, if you want to get the acceleration, you take the derivative of velocity, all right? So this d squared x over dt squared, what it's simply saying is that, all right, get a little dealio there. All right. So this equation where you have d squared x over dt squared, all it's saying is that this is the acceleration of the object. First, we started out with x, the distance of the proton horizontal to the left or to the right of that vertical trajectory down the middle of the quadrupole magnets, okay? And its dependence upon time, that's velocity, dx over dt, that's velocity. That's how fast it's moving left and right compared to going down the middle of that z-axis in the quadrupole. And then how much the velocity changes with respect to time, that's acceleration, okay? So in calculus, the acceleration of an object is the second derivative of the position of that object, dx squared, with respect to time, dt squared, okay? All right? And it just sounds really mumbly-jumbly. Acceleration is also the first derivative of the velocity, right? And it's the second derivative of the position, all with respect to time. Mathematical tools, everybody. Calculus. Mathematical tools to describe position, velocity, and acceleration with respect to time. Okay? All right. That's what this dx squared over dt squared means. It's the acceleration of the proton in phase space horizontally to its trajectory around the proton accelerator with respect to time, okay? But it's that same equation, mass times acceleration. Acceleration here is the acceleration of the proton in phase space horizontal to that central trajectory with respect to time, all right?